Okay. Okay, good morning, everybody. So what we will do is we'll start with the homework that we have given. At least one of them we will just solve it, and then later we will proceed with the decompositions. So that's the plan. Okay. So yesterday what we did, actually, I have given one homework of actually Gram-Smith orthogonalization process, right? Yeah. Is the spelling correct? Huh? Smith. G A. Correct only. No? No, I should stop on spelling it. I always miss spelling. SCHMIDT. That's correct. Just the H is not there. I believe I given one, and I think set of vectors. Let me check. Yeah. Yes. Let me take them. So this was the question. And let's solve it. So the formula is very simple. If you have a V1, V2, V3, and so on, are the vectors, then if you have to orthogonalize it, all that you have to do is take the first vector as it is. So step one as it is. And the second vector onwards, how is that? So the first one is as it is. But the second one onwards, V1 minus, sorry, not V1 minus, V2 minus the projection of V2 on V1. Yeah. So that's the second vector. And the third vector will be V3 minus projection of V3 on V1 minus projection of V3 V2. Is that okay? So this is the way actually we have to keep doing it. And then if you have to orthonormalize it, then every time what you also have to do it, you have to normalize them. That's the only process. Okay. Or finally also you can normalize it. Nothing different than that. All of them are okay with that. So what we did is actually, remember, we had a projection function which will give us a vector. Did I take V or U? I don't want to confuse you. Yeah, V and U, I guess, right? So this will give me a projection of V onto U. That's the terminology we had. And then what did we do? Actually, now I returned. We take the dot product of U and V and divide by its norm. Divide by the norm of U square. So this will give you the corresponding scalar for me, and then multiply that with U. You will get the projection. Okay, fine. So let me take the S is equal to, all of them are vectors in my hand, so I can pick up them and then put it. Okay, so the, let's call it as U1 or something, whatever. Yeah. So V1 equal to first vector. What's the first vector? I have that vector right now, 2, comma minus 1 comma 3 comma 1, and then the second vector is equal to 3 comma 3 comma 4 comma 0. You would have typed it yesterday, I guess, right? I don't want to waste time in typing it just like that. So 1 comma minus 2 comma 0 comma minus 1, and the other one is 4 5 5 minus 1. So as you know, what we will do, you will keep the u1 as v1 as it is, or you divide by the norm. So the norm of v1, and that's all, correct? Now, if you give u1, then it gives me like this. Now, what you can also do is you can, this is actually real computation, with real precision. But if you wanted a approximation, then what you can also do is you can convert this norm into a floating number. So the easy way of doing it is just to write a numerical approximation of this by using this dot n of function. Okay, that will give you a numerical approximation. Otherwise, you can leave it as it is. So I'm okay with anything, whatever you feel like. So we use this for classes and all. Okay. So then what is your U2? U2 will be whatever V2 you have minus then projection of U2 on U1. Am I right? Okay, projection of V2 on. So if I print U2, I'll get this. Yeah, like I can normalize it. So finally, you can also actually take the same vector, entire vector, and then divide by the norm. The one easy way of doing it is just another time actually you do U2, but this time actually you take the U2 and then find the norm and then do that. Yeah, actually U2 divided by U2 divided by U2 divided by U2's norm. Yeah, norm of U2. So I'm alternatively using it. You can see that here I have used norm of U and here I have used dot norm of. So as I already told you, the SageMax follows the object-oriented programming. Either you apply the method just like that as it is, or you call the function on the object instance, and that's okay. Both will work. Okay. So likewise, you can find U3, U4, etc. But as you know, we would like to write a function. That was the question. So why don't you write a function? So now let's write the function Gram-Smith. And what it's supposed to take? It's supposed to take the S as the input, meaning the set of vectors is an input, and it's supposed to return the final one. Okay. Fine. So now we are comfortable in actually computing the length of the set, and then we know how to call each people by its name, by its index, etc. So let's use them. Now, if I have to call V1, then I do not have to call V1 as it is like that. We can actually call them as S of 0. So because assuming that S is the S is containing all the vectors in hands, right? So now Gram-Smith of S is equal to Gram-Smith of S will first actually calculate the number of vectors in it, and then let me start let me start. What I'm doing now is, we know that the first vector will be the first vector as it is, maybe divided by its norm, correct? And I'm going to keep adding, I'm going to generate a set, and then I'm going to keep adding that vectors, what I'm generating in the next to that set. So the way easily you can perform is just first create an empty set like that, and then throw every vector that you generate into that set or into that array. So that's how it works. Yeah. Our finance minister has come. Okay. So E, as you know, the first one I am going to throw inside is the S of 0, the first vector itself. And maybe with the norm of S of 0, right? Divided by the norm of S of 0. Hopefully that's clear. Yeah. Or with the numerical approximation, all of them. So all that's up to you to decide. I'm going to just stick to the real computation. After that, we will come back and change the numbers. Now what I have to do now, for the remaining vectors, that means for I in the for k in the range of 1 to n. 1 means the first vector has already been dealt with, so not bothered about that. So I start with 1 and go until n. That means I'm going until n minus 1. Right? So that means until the end of the set. I'm going to create, or I'm going to generate a function like that, meaning I would generate a Q, which will be the current vector what I am looking at minus just before that vector, whatever was there, you take all of them and find a projection of this vector onto all of them and then sum them up and subtract it. Is that okay? Yeah. So it's literally what you have to do is you have to find the projection of V2. If you are at kth element, that means you have to take the Vk and then you have to project it on Vk minus 1. Then subtract projection of Vk on Vk minus 2, etc. So hopefully you understand. So instead of doing this way, what you can also do is you find the projection on all of them and then take the sum of those projections and then subtract it. Okay. So along the way, you can also divide by its norm, or after that also you can divide its norm. So all of them are, it's very handy to do that. So I'm going to do that. So what I'm going to do that now is, as I already told you, I wanted to do the projection of Sk, meaning S of k, on what? On what? On every element that I have actually generated previously. That is actually sitting in E. Did you notice? Yeah. So the E of I will give you that. And I need this projection for everybody. So what I'm going to do is I'm going to use the list comprehension. Somebody can check whether the Zoom is okay or not. Because I was asked to join internet. So Zoom is working fine. Yeah. Oh. So I'm going to use a list comprehension, which has already been introduced by Dr. Vinay in the last session. I have to do this projection for all I in the range of k, correct? I don't know. Is it understood? Yeah. I haven't actually summed them up still. I'm generating a list of all people where the projections are actually been done of the vector S of k onto everybody who is there in the E. Remember, actually in the E, actually we keep adding it. That was our plan. Okay. Fine. Hopefully you will understand what I'm saying. So this one is the list comprehension. So what it does is actually for I in range of k, that means, remember actually currently I am in 1. That means it's going to do only for the first element in the E, and it's going to find the projection of V2 on V1. Yes. Yeah. In the next step, of course, we'll be adding the projection to the E. Yeah. So what also we have to do? we also have to append the Q that we have generated to that E. Is that okay? Yeah. So now this up to you right now. Either if you want to ortho normalize it, while you are appending, actually, you can also divide by its norm and then append it. Okay, fine. It's just 2 lines of code only. Okay. So finally, what we want after this is the process that we have to do. And remember, actually, I forgot one more thing, that I have actually subtracting the list, which is not what we want. What we wanted was we generated the list of all the projections and we want to sum them up, and then we wanted to subtract it. So actually, we want to subtract individually. So sum of that list. So sum of that list will give you the sum of all the vectors which is there, and therefore now it will be 1. Okay. Of course, I have to return the E later. Okay. Fine. So now let's put up the S here. Now S is a list of all vectors. Now remember, actually, I have V1, V2, V3 here. Maybe I'll copy this and then paste it here. I can put each vector over here and then put a comma, etc. But I already have the names, so why not you use that names? So now if we look at S, then these are the vectors in my hand. Now what we can do is, now we can run a Gram-Smith method on this S. And now that returns a set of vectors which are orthonormal in nature. It has to be, you can probably check, maybe we'll write E is equal to, and then print E also. And then the way first thing actually we'll check is just take the E of 0 and then do a dot product with the E of 1. That's it. That means the first 2 vectors are linearly independent. And you can try doing that for every combination, right? So E of 1, E of 2. So that's again 0, etc., etc. And not just that, the way actually we have constructed, we have also made sure that the every vector which we have generated was divided by its norm. Therefore, all of the vectors which are sitting in E are orthonormal, not just orthogonal. Okay, so that's clear for you. That also you can verify if you want. So you take the E of 0 and then find the norm of it, and that's 1. Yeah. Similarly, anything in the set will have the norm of 1. Normalized. Clear for everybody? Okay. Analysis. Yes. Why is here? Okay. That's it. So now what we will do is we'll look at principal component analysis and some more decompositions, whatever possible. Then later we'll go ahead with that. Okay. Maybe before principal component analysis, I will show you some decompositions, whatever you wanted to do is all already available. If you, let's say, suppose you have a matrix A sitting on Q, it's a large matrix. Huh? Ah. Can you briefly explain this once again? Yeah, which part? Like the Gram-Smith part, I believe. What I have done here is I'll just show the function. I think that's enough to have a look at it. So what we did right now here is we started with the first vector, and then we add the orthogonal vectors to that every time. So we generate a vector V, we generate a set E by the first vector, and then the next vector that I'm trying to throw in to that E will be orthogonal to that. And then the next vector that I'm trying to throw in will be orthogonal to both of them, which are already there. So that's the plan. So the way you construct it using Gram-Smith or orthogonalization process is that you take the current vector, what you have, and project that current vector on everybody who is there in the set. And then you subtract all of these people from S of k. Then what will happen? You will actually have a vector which is orthogonal to all of these people. That we have seen in the last class, correct? So the way actually you generate a orthogonal vector is just look at all the linear combination of the bases, and you meaning you find the projection of all of projection of the vector that you are having in your hand with all of these people, and then sum of them, take the sum of them, and then subtract the sum from the original vector that you have in your hand, and that will become normal to that space itself completely. So that's what we have done here. So we found the projection, and then what we did here is we did it for everybody who is sitting already in the E. That's what we have done. So this I was running that index. Yeah. And then what we did, all of these projections we summed up. That's what we have done. And then instead of me subtracting every time the projections, what I have done right now here is I summed up all the projections and then subtracted. I think it's all same. Yeah. I subtracted from the S of k. And once I do that, that current vector, I'm actually keep adding it. So that I'm doing it until I'm exhausted with my all the vectors in my hand. That's all. And then finally, once I'm exhausted, then I'll return the E. Yeah. So that's how it works. So that's a Gram-Smith. Okay. Good. Okay. So let's generate a vector for now. Then later we'll try finding it. I think it is. So 1 minus 1, 0, 2, 4, 7, minus 1. And then 2 minus 1, 0, 6, 4, 8, minus 2. Then 2, 0, 1, 4, 2, 0, 1, 4, 2, 6, 0, 2, 6, 0. That's correct. And then 1, 0, minus 1, 8, minus 1, minus 1, minus 3, 1, comma, 1, comma, 2, comma, minus 2, then minus 1, comma, 1, comma, 3. Yeah, don't forget the bracket. That's my So 1 minus 1 0 2 4 7 minus 1 2 1 minus 1 0 6 4 8 minus 2 2 0 1 4 2 6 0 1 0 minus 1 8 minus 1 minus 1 minus 3 1 1 it's not 12, it's supposed to be 2 2 minus 2 minus 1 1 3. Yeah, okay. Okay, so all of you type the matrix. So any basic decompositions that you are thinking of is already available in Sage Math. Like for example, if you have to look at the LU decomposition of this matrix, then all that you have to do is A dot. Then if you press a tab, then you will have the list of functions available that you can operate it on A, correct? Now your intuition must say that as this L, I mean the function should start with the LU decompositions L. So just press L, then you have this function here, right? Okay. Now, if you put a question mark, obviously, and then run the cell, then it should give you a explanation as to what and what has to be given. I think probably I should have taken this example as it is. When you run a dot LU off, then what it gives you the three matrices. One is the permutation matrix that has been used, the product of the elementary matrices that is required for the LU to work, and then the lower triangular matrix, and then the upper triangle. So that's the three matrices which has been returned when you are actually running this function, correct? So you go up. Yeah. So if I run this, now you can see that the first one is the permutation matrix, and then the second one is the lower triangular matrix, and the third one is the upper triangular matrix. So I can pick them up by writing P comma L comma U is equal to like this. So this is a destructuring which we have already seen in the previous things, right? So if I do a show of P, and that's the permutation matrix, and then if I do a show of L, and that's the lower triangular matrix, and then if I do a show of U, and that's the upper triangular matrix. Okay. So there are some optional stuffs like you can do partial, you can do compact version of this, all of them. Like for example, if you have a, yeah, I think we should do it separately. If you have LU equal to, and you look at the options here, you see that pivot, and it has a pivot strategy. So pivot strategy has multiple options. So one of them is auto. So it says if the matrix entries are ordered, and if so, use the partial pivoting strategy. That's what this says. And partial meaning actually each column is examined for the element with the largest absolute value, and the row containing this element is swapped into that place. So what we usually do it in LU decomposition. So I don't want to go into much detail of that. Whenever we wanted that the column to have the largest element in the pivotal element, so we'll swap that columns, right? Remember, the same thing is being done here. Okay, fine. So if you write pivot equal to partial, then that gives you the appropriately. Okay, fine. And I believe there is also a compact version of it under, I think, format. So under format, if you give a compact version, and that gives you simply the permutation matrix and the whole matrix as it is. Like from this, actually, you can figure it out who is L, who is U, right? You see the lower portion is obviously L, and along with all the diagonal elements should be 1. Okay. probably what I'll do is I'll catch these people as partial. Okay, I'll write it as C here, and I'll tell you what is this. So here is. So now you can see all these numbers, whatever is there in the diagonal, are all actually coming from the upper triangular matrix, and all of them which is in the lower portion is coming from the lower triangular matrix. So if we are to split it, then you simply take the L and replace all the diagonal elements with 1. And the other upper triangular matrix, you as it is, take it with the diagonal, and that will give you U, right? Just a compact version of looking into it. So similarly, you have all the decomposition functions are available. For example, you have a matrix and you wanted to have Cholesky decomposition, for example. Where is that? Okay. Not creating the, yes. Where is that? Don't. I think my computer hanged. Just a minute. Yes. Okay. Sorry for that. I think for the past 3 days, the kernel is keep running, so it got confused. I don't know why. Okay. So if you have to do a Cholesky decomposition, you know what is it? It's like this is just an LU decomposition of a positive definite matrix, right? That's all. So you also know that actually it will be L into L star or L into L transpose. So any matrix, if we could write it as L into L transpose, then that that decomposition is actually called as Cholesky decomposition. Yeah, I don't know where it went now. I just typed it. Yeah. So for that, first of all, I should check whether it is a positive, whether it's a symmetric or not first. So let's take one small example, 4 minus 2, 4, 2. Then minus 2, 10, minus 2, 7. Four minus 2, 8, 4, 2 minus 7, 4, 7. Okay. That's the matrix. Obviously, this is symmetric. So now what we can do is we can first check whether it is symmetric or not by running A dot is symmetric. Okay. By looking at it, you can obviously figure it out, but programmatically, you have to figure it out sometimes when you are running into loop or something. Then I can run a Cholesky decomposition. You know, if I press A dot and then tab, then it gives me all the functions which are available. Okay, symmetric is not there. That's because I think I made a mistake in the entry now. It's now. It's, yeah, thank you. So it's symmetric now. And then now if I press LA dot Cholesky off, then that will give me the L. And therefore now what we can do actually, and we'll probably catch this fellow. And then It's not creating a thing wrong with it. I don't know, some weird thing is happening. That's correct. I'll add some cells automatically first, then later we'll do. So many empty cells, but somehow they are not visible to me. Very weird. Running in the, huh? Seems to be what? RAM. But okay, probably I'll close everything. Yeah. Okay. Yes. Now it should act properly, I guess. Okay, no problem. Just one more time, I'll refresh this page so that it will listen to what I say. Okay. Yeah. So I just have to multiply L into L transpose and see. I know this is just a real matrix, so that should be okay. Now, whether that is equal to A or not, that's all I have to check. And it's true. Yeah. Good. Huh? It's working now. Yes. Yes. Oh, perfect. One more time, if this is misbehaving with me, then probably I have to change the laptop. Okay. So similarly, you can look at the QR decomposition. You already know what is QR decomposition means. The QR decomposition is nothing but you just look at the corresponding uh, orthogonal matrix and then take all the orthogonal vectors as a cube. That's it. Okay. And R you can find it appropriately. So you take any U and then try finding QR decomposition of it. And that should give me the QR decomposition. What I have done here, QR decomposition unable to compute square root of rational field. Yes, that is because you see that A that I have actually is generated is actually on rational numbers. So obviously it has a problem. So what we can do is, as we have mentioned in the last class, you can use an algebraically closed field to avoid all of them. So okay, maybe for these kind of computations, you can work with the fixed point fixed point algorithmics, arithmetics, right? So I do not have to actually very strict on real precisions. So we can try with CDF, this algebraically closed field. Where is that now? Yeah, yeah. Then it works. Yeah. So initially it was not working because I have rational field. Now I have used any algebraically closed field. I think if I'm not wrong, I have it in my notes. Actually, there's also QQ bar, which is algebraically closed. Yeah. You can use that as well. Okay. So I'll restart the kernel once. Because let's see. Is it okay? Any doubts until now so far? So whatever we have done now so far is we have tried to do an LE decomposition and it was perfect. And then Cholesky and then QR. Any other decomposition that you can think of in your life, you can actually try doing it in the try looking at it in the documentation, and that should be mostly available. Okay, fine. Okay. So now what will I do is I'll do a SVD and then try doing some application of SVD. Yeah, similar value decompositions. So I would have already shared one image in the group. Yeah. Let's see whether time permits or not for principal component analysis. Let's do LCD. It's already 10:50. Okay. So you already know what is SVD is. SVD is very simple. It's just you look at the any matrix. It's just a counterpart of spectral decomposition. If your matrix is not symmetric, then the spectral decomposition will not work. Therefore, we go for singular value decomposition. So any real matrix actually has a singular value decomposition, where the eigenvectors and eigenvalues, all of them are dealt with A transpose instead of A. Because A transpose becomes square and symmetric, all of them are there. So we'll find the eigenvalues, all of them, and then square root of their eigenvalues becomes singular values. And now when you write matrix A, you can have U and then sigma V transpose, and that will become your singular value decomposition, correct? Okay, so the sigma will have all the singular values as a diagonal matrix, and then you will have the eigenvectors of A transpose, and V will have eigenvectors of A transpose, etc. Okay, yeah, or the other way around. I don't remember now exactly. I think both will work. So now what I am going to do is I'm going to use this kind of decompositions and then on a particular image, and then we'll come up with that actually now what does that give to us. Okay. So first of all, what is an image? Anybody have any idea about this? Yeah. So image is just an array of matrix elements. You have heard of it? Any image that you are seeing it in phone or anywhere else, it just actually is a matrix where each entry will represent the pixel. Each entry is actually called as a pixel value, and they represent the color of that image. So if it is a grayscale image, then they have the image number, first of all, actually starts with 0 and then go until 255. So that's the color range. Okay. Now, red also can go until this range, and then green also can go until this range, until in this range, and then blue also can go until this range. So any combination of these things will give you a color. So that's how it works. Okay. If you go into any online tool to look into it, an RGB color space, for example. Yeah, you can see that from here that you have a number between 0 to 255. Now that color over here has been appearing here. I mean, can you notice? So the numbers between 0 to 255 only is here. So now I have a 255, 255, 255, which represents the white color here. Okay. So if I change this to 0, and you see entirely different color. If I change this also to be 0, then that becomes blue. So this is the blue we have. And if I make this 0, and then this is 255, and that gives you the green. And if this is 0, and then this is 255, and that becomes red. Okay. Now let's say we have some combination of this. Let's say this is 100, this is 100, and this is 100. Now you can see that some gray color is coming up, and that's a mixture of all these three colors. So R, G, and B. Okay. So now to represent these values, so let's say this one is having 10, this one is having actually let's say 200, This one is having, let's say, 100. Okay. So now this is, you can see that actually now what is that is more now? More is the green. So you can see the color is also actually greenish. Okay. So it's not exactly green, but it's a mixture of some portion of green is there, some portion of more portion of green is there, and some portion of red is there, and partially blue is also there. Okay. Now, if I reduce that also to be, let's say, 0 or something, then you can see that it's more of a just a green only. Okay. So that's how these colors changes. So for mentioning every single pixel in my image, then I need 3 values. So is that clear now? Yeah. So you have a 2-dimensional array. In that 2-dimensional array, what I need is in each entry, instead of having 1 entry in my 2-dimensional array, what I need is actually I need 3 entries in the 2-dimensional array. Yeah. So we call this as a multi-dimensional arrays. Hopefully you're understanding what I'm saying, right? So how will I have it now? So in my matrix now, instead of me having an matrix like this, instead of me having 1, 2, 3 like that, now what will I have? At this place 1 itself, I will have an array where this will tell me what portion of red, what portion of green, and what portion of blue is there. Similarly, instead of me having only one number over there, I'll have an array in which this will tell me what portion of red is this, and what portion of green is this, and what portion of um, blue is this. So instead of me having blue, meaning 3 there, then this will tell me what portion of red, and what portion of green, and what portion of blue is there. Okay. Hopefully you understand. Okay. So obviously this will not be a matrix of because as I already told you. So Sage has no support like that. I believe I have typed it correctly. I believe yes. Yes, that's correct only. So what I'm going to do is I'm going to switch it to something which is going to give me support for that, which is a package called NumPy. So I think this is the first time actually I'm importing something in SageMath. This is the way that actually you import any package into a SageMath. This generic notation of using Python's way of importing the packages. Now, NumPy is it stands for numerical Python, numerical computations of Python. So it's mostly doing all the matrix related operations. Okay. So it's a kind of package which will help us to do some vectorized computations. Yeah. So very fast and very easily you can do it. There are powerful things are already there. Now, NumPy is already installed in your computer if you have already SageMath installed, because SageMath actually built some matrix operations on top of NumPy only. So it has already automatically installed. So the way actually you generate a NumPy array is simply instead of matrix of, then you write np.array of. Okay, so that's it. You got the idea? So instead of matrix of, you make that as np.array of, that will work. Now remember, I also have brought this NumPy with an alias of np, and this is called as aliasing or aliasing. Okay. So what is this? This is actually saying that I bring the package NumPy in the name np. So anytime now I wanted to call some function from NumPy, I will call it as np dot whatever the function is. Okay. For example, if I have to sum this array, then I say np dot sum of a, like that. So this function is defined in NumPy separately. Okay. So that's the idea. So np dot, I think len is there. No, len is not there. I think length. No, that's also not there. No. I don't remember now what other functions are there. I think unique is there. Yes, unique is there. So now I can find unique values of a just like this by calling this. Hopefully you understand. This is also obviously object oriented. That means I can also call the unique function just like this on an object. Okay, this is not there, but what is happening? I don't, I have to check. Okay, sorry for that. This is only works now. Supposed to work. I don't know why it's not working. Let me check. So for now, we'll use this. So np.unique will do the unique values in this. So you can see that 20, 45, 100, and then 255. Everything else is actually same. Now this is so powerful that it is actually dwelled down into all the elements in the arrays. If you look at that array, it's not a two-dimensional array anymore. Now in you can think of as a slices. So the first slice will have the values 20, 100, and 20, and the second slice will have 100, 20, and then 100, and the third slice will have 45, 45, and 255. So these things, what we'll also call that is these slices, we will call that as a channels. So red channel, green channel, blue channel, like that. So that's how the image is. Okay, fine. Now, along with this NumPy, I also would like to import something matplotlib dot pyplot. This also is installed in your SageMath along with SageMath, because all the plottings in SageMath has been done using matplotlib. Now I specifically wanted to use some functions from matplotlib, so I bring them with some alias names like that. Okay. Otherwise, what will happen is SageMath would have already altered some function of matplotlib to specifically do some like, for example, plotting a vector is never a function in Python or matplotlib. So if you simply say plot, then the plot from the SageMath will be active, which I do not want. I wanted a fresh installations. Okay, that's it. So I believe I can do an IM show on the image. I guess yes. Yeah. So now can you see what's happening here? So what is happening here is, now if I write plt.imshow of A, it takes the matrix array like this, and it gives me the corresponding image. Okay, let me delete the middle one so that I can keep everything together. Yeah. So what is this now? So this is now, it's never been actually now considered as a matrix itself. It has been now considered as an image, and then the image has been printed over here. Now you can see clearly what is happening here is, this is a red, this is blue, sorry, green and blue, right? So 100 is obviously more, therefore more green is there. And then even if you want, actually you can take this numbers and then understand what is this. I'll put this also inside this so that, yeah. Is that okay? Let me zoom out a bit slightly. Yes. So then that's the green. And then this one is, okay, probably we'll start with the red. Huh? So 255, 0, 0, then 0. 255 is the maximum number. Okay. 0, 255, 0, 0, 0, 255. Yeah, can you see that now? So the first entry is representing only the red color. The second entry is representing only the green color. The third entry is representing the blue color. Okay. Yeah. So any images now, you can think of that as simply a combination of these colors only. So now what we can do, I can actually put one more row like that. And that is actually already started realizing that actually that start doing a matrix. So that start building the image for me. Okay. Now maybe if I change this to 0, then 50, you will realize it. So you see that. So a combination of these colors only actually forms the image. I will actually tell you, I will show you by looking at one image. Yeah. So now you can fiddle with actually creating some colors if you want. Okay. No, that's not one. Hopefully you understand what's going on. Yeah. So similarly, what you can do now, you can increase your matrix width and then the height. And in each entry, now you put a three-dimensional array. And that three-dimensional array, the first value should represent the red portion of it. Then second value should represent the green portion of it. And the third value should represent the blue portion of it. And then the image is actually automatically created like that. Okay. Fine. Now there are two types of images in general. One is a color image. The other one is grayscale image. Now what is a grayscale image? Now remember, actually, I have created a array. And in that array, what I did, actually, I placed three people inside. So instead of me placing three people inside, if I, let's say, suppose place only one person in that place. And then now if I do plt dot im show of A, and now that gives me something different. Yeah. Now you see this 100, 100, 100 actually gives you the yellow color, and then this. I think what is trying to do is it's trying to do some map here. I think what is it? C map, C map. So if I do a C map and then tell it to consider that as a grayscale image, otherwise what Matplotlib will usually try to do is it will try to give different colors, so which we do not want it. So if I do this way, then it gives you the exact way of looking at it. So it's a gray map, a gray color. So I do not actually have any other colors to visually look into it. That's the idea. Now you can see that this right now says the first row entry says the first three cells over here. So the first one is just 100, and then the other one is 0 and 0. So I have already told you 255 represents 100 white and 0 represents the black. Then anything between them will represent the shade of it. Okay. So now if I, let's say, change it to 150 here and then 200 here, then probably you will start realizing what's going on. Yeah. So the first cell is actually a 100, then 150, and then 255. Yeah. So slowly you can realize it. So slowly you can change and then see. Let's say 125, 175, and then 225. So this is different shade. And then now 150, or maybe I'll do 50, 75, 125, or whatever it is number. Yeah. Nice image we have created. So now what we have is a grayscale image. That's it. Yeah. Clear? Everybody's okay with that, right? Shall we move ahead? Yeah. So given any image, now if you look at it now, what I have is just a 9 by 9 matrix, which means only 9 values are possible in my hand. So what is the size of this image? You can calculate it like this, because anytime what we have, we wanted to actually store that image into a computer, and how is that been done? It is just by storing the numbers like that. There are other ways, there are other methods of compressing it. Right now, I'm not going to bother about it. I'm going to look at something called as a raw size of the image. Then if you save that as in a JPEG image, if you save that in a PNG image, if you save it as a PDF, if you save it as a EPS, so all of them are different formats of saving them, and they have their own way of compressing the files and then putting them together. So I'm not going to consider them right now for now. I'm just going to consider something called as the raw size of the image. So no matter from which format you're reading it, once you read it, then it will become a matrix, and then that matrix will have some memory in size. And what is that size of that matrix is requirement? Okay, that's it. So in computer science, you generally, if you look at it, they will tell you any integer, if you save it, then depending on what integer it is, whether it is a small integer or double integer or a long integer, they have the size that they can actually, they have the prescribed size that will take in the memory. Okay, for example, any number between any 3-digit number, if you have, then they can be represented by 3-bit representation like that. Not 3-digit number, any number between 0 to 255. If you look at it, they can be represented by an 8-bit representation, 2 power 3. Yeah. Okay. And if I'm not wrong, 8-bit is 1 byte, I guess. How much is that 1 byte? I don't remember. Vinay, can you tell me? 8-bit is 1 byte, right? Yeah. So 8-bit is actually 1 byte. So if all that numbers now, whatever we have is actually 0 to 255, that means we need only 8 bits of memory right now, for example. Then 1 byte is required for every entry individually. That means how many entries we have totally in a binary image like this, in a not binary image, grayscale image like this. We have total 9 entries. So 9 into 1 byte is required, correct? So totally that much is required. Suppose if you have a matrix of size, let's say 1000 by 1500, then what's the size of the image you need? What's the size of the image will be? The raw size of the image will be 1000 by 1000 matrix will have 1000 by 1000 into 1500 entries, and that much memory I needed, correct? So this will be 1000 into 1500 bytes I need. Okay, that means I need 1000 into 1500. Now, I can do one thing. I can divide by 1024, and so what will happen is it will give me in a kilobytes. That means this much KB is required. I can further divide by 1024, and that will give me in MB. So 1.4 MB is required to store an image of size 1000 by 1500. So these many pixels are there. Therefore, we need this much memory is there. Okay, these are rough calculations. So this is the idea of calculation. Okay, every time when you try to change it in, save it in some other format, they have their own compression of doing it. Therefore, this memory may not actually really occurring in your storage device, because you would have saved it in a JPEG. You would have already realized it for your research works and all. Even when I was saying that if you wanted that image to be scalable, then you store it in EPS format or PNG format. So image is image. Then you storing it into some other format will change the way it acts. It change the way actually it is stored in the computer. So I'm not talking about that right now. No, hopefully you understand. I'm talking about once you read it from the any file you have, then you will have still 1000 by 1500 matrix, and to store that matrix in your temporary memory in a RAM, then how much memory is required? How much is required? So that is what is being calculated. Exact. What is it? Chat. Okay, sorry. Yeah. How did you type that sigma in the equation? Last one. Okay. Can you post a screenshot of the code and the okay. Probably he wouldn't have actually given this CMAP. Huh? That's what the CMAP is not there. If you actually just copy this and then paste it, let me say. Then this will look like this only, as I already explained. by default, Matplotlib will try to actually feed some colors into it. So we'll tell them not to do so by CMap. That's all. Yeah. Okay. Anyway, I'll delete this. That answers the question. Okay. So this is the memory size that we needed. So this is important because our aim of actually is doing this SVD on that image is to actually somehow reduce this size. We call it as image compression. Okay. So I do not do image compression lossless. I am going to do lossy image compression only. However, how much I can lose is the question mark, and that I can, of course, somehow convince myself that comfortably you can leave some of them. Yeah, so that's the idea of doing it. Okay, fine. Okay, so let's do that. Now we have an image in my hand right now, like this 9 by 9 image. Maybe I also have given you some images in the WhatsApp group, I guess. You can download them and then bring it to a computer. Okay. Now, if you have found the Sage Home, if you are in the Windows machine, if you find the Sage Home, then one way of doing it is actually just throw that image into that Sage Home. Just put that image into the Sage Home. You can see now what I have is in my session, in my laptop, I have something like this in my folder. I don't know how do I zoom this. I don't think so. I can zoom this, fellows. Okay. And then I have a folder called images, and under that I have some images over here. Okay. So I'm going to use them for now. Okay. And I think I also have a gray image which is sitting here, which is, yeah, that's it. Let me actually stick to this images folder. I am right now, my file is actually session 9 IPython file. So along with my file, I have an image folder, and then under that image folder, I have all of these files in my hand. Okay. Hopefully you understand the folder structure. Okay. So I'm going to use this. Now what I can do now is I can bring this image and then try looking at them instead of me constructing the image like this and then looking at this view. Okay. Fine. So the way you do that is you can install you can use the function called imread from matplotlib. So for that you need matplotlib first of all. So what I can do is now import matplotlib dot image. Okay, maybe I'll do one thing. I'll just import the function only. So from matplotlib dot image, import only the imread function. That's it. So I'm importing the function called imread from the function from the library. Yeah. Now what I can do is I can read this image using this function by providing the path of that image. Remember, currently I am in a folder where my IPython file is also there, and in that folder we have a images folder, and then we have the file name over here. I believe if I press tab, that automatically that should tell you what are the files there in your hand. Okay, so if I press this, and then it should tell you if you read that function, meaning if you compile that cell, that should give you an array. Now, hopefully, actually, now you get comfortable with actually what are these numbers mean. Yeah, when I read an image, then what is this? This is just an array of numbers. And these numbers are between 0 to 255, you already know. And the first, for example, the first cell has 190, 190, 190. Yeah. Is that comfortable for everybody? Yeah. So I'll do one thing. I'll just store it as an img variable, and I'll use that for further computations. So maybe this is the first, this is first row, I guess. Yes, first row. You can try plotting that by imshow. I think plt.imshow. image. And that's the image I have picked up. Yeah. Now, you see, you can actually take anything you want. For example, here, let's say I'll take only the first row or first 2 rows or 3 rows, and I'll take every column from there. I think that will work. And what I will do, I'll try printing only that much. Okay. So plt.im show of that much only. Yeah. So I think 3 is too much, 2 less. Oh, this image is actually, how much is that image? Can you say? Can you see that? What is the size of the image? Maybe I have an image function, so I can run a. Do I have a shape function? Yes. So I can run a shape function on that. Actually, it's an attribute. Every NumPy array will have this attribute called shape that will give you what is the size of the array, and then in each cell, what's that dimension of the array sitting in right now, right? So for example, here 570 by 720 is the size of the array. That means the matrix size is 570 by 720, 570 width, and then 720 height. 570 height and then 720 width. And then in each place, 3 values are there. That's what it says. Okay. So now if I set there, suppose 100, if I pick it up, then can you see that the top 100 rows have been picked up and that much only has been visible now, correct? This is what we mean by cropping. Cropping is simply you pick up some of the rows and then do it. Let's say suppose I pick up starting from 100 and then I'll pick up until 200. Is that okay? Huh? Charger? Sorry, I have to charge. So this is simply cropping. I'm just taking the first, I'm taking some 100 rows between, okay? Now you can fiddle with it and try finding it, what will be the cropped image. Now, remember the way actually I call this is, I took the rows and in which I have a colon between that. So that will tell what's the starting value of the row that we want to pick up and what's the ending value of the row. And I have a comma here and I left it free. That means I want all the columns. So you can also bring the columns. So let's say, suppose I have a place, let's say 200 to 500. Okay. So you can also put the 200 to 500 here. And now that will give me a nice cropped version of it. Okay. So hopefully this much amount of basics on images is enough, I guess. So all of you are comfortable now? If you say yes like this, then no. Yeah. Not coming? Huh? Image, what is the problem? Huh? Code, which one? This one, right? Yes. I don't know, something is wrong with that. Where is when everything is white now? Yeah. So you have to place the image in the right place and then call them. So what we have done right now is just cropping the image. That's all we have done. Now you know linear algebra. If you want to rotate an image, now you know what to do. What do you have to do? Transpose. Yeah, you can do that. You can try finding the transpose of it and then print it. So try doing that. It's very simple to do. Now, you know, this IMG is just a matrix now. I believe T of, I don't remember. What is the function on pi array? Oh, we can't do it on, no, it's a matrix actually. But yeah, but there's a way of doing it. Like you have to rotate, you have to take a transpose in a particular axis. Because it's everything is cell, no? Huh? Huh? Yes. Yes, correct. Which one? That should work actually, yes. Anyway, you just pick up only one channel, that should work. Now, technically, actually, as although I'm showing a green channel, grayscale image, it is actually a color image if you look at it very carefully. Because it will have red channel, green channel, blue channel. Okay. So that's just a cropping. I will have some other images as well. Remember, I think I would have also given you some images like this. Yeah. So this is one color image we have. Now I am read. Now remember, my images are actually in the images, and then now I have a sample. Samples, I guess, with a capital S. Samples, and then under that I have a dog one image. Yeah. Okay. So that's again, it's a array of numbers only. So let me store it as dog, and then plt dot im show dog. Clear? Three little cute puppies. Did you bring it in? Is it okay? Working? Huh? Yeah, any format. You can read any format. That's what I said. Whatever the format is your file is stored, then once you have the file read, this is just a matrix of numbers. Once it has become a matrix of numbers, then your memory is actually going to store the numbers only. Yeah. Right now, currently the RAM will have that much memory. Now, this size of this matrix is very simple. Just you look at the height and then the width. So it's actually too big array now. If you look at that size here, dog dot shape of the images. It's 1600 by 2560. So what should be the size of the image? We have already calculated. It's just 1600 and then 2560 and divided by 1024.0 will give you this much KB. And then one more time you divide by 1024, it should give me the MB. So originally this image is supposed to have 3.906 MB. In your device, it will be lesser, but that's just the size is required in the RAM for sure. So this much MB is required. So size of this image. Yeah. There's a better way of calculating it. I'm not doing it right now. So it's easier to just look at that. So let's keep this image right now for now. And now let's proceed forward for grayscaling this image and then proceeding with SVD. Okay. So now I can look at the different color channels separately. Probably what will I do now is I'll just look at one simple, I'll just generate one simple matrix, and then I'll show you what are the color channels we have. Remember what we have? What we have is, if I suppose write like this, then what does this mean? By the way, what we can also do is, for any other computations, what we have, 0 to 255 is not a good number. So what we usually do is we'll normalize that numbers between 0 to 1. And therefore it becomes a real number, and therefore we can do computations properly. So 0 to 255 is not a good number for any computations that what we wanted to do. And therefore what we will do is we'll convert them into a normalized number array like that. So abrupt divisions. There are multiple way of actually normalizing the numbers like that. Take the maximum and then divide by its maximum and subtract the minimum. So many other ways of there. But now to make it very simple, let's say we divide by 255. So instead of me writing 255 now, I can actually write 1 as well. That's okay. Yeah. And then let's say if I say 0, 1, 0, then that means the same thing. Like the first one is red and the second one is green and the third one is going to be blue. Okay. So now let's say I store this as an image, and then plt.im show image. This will give me, what did I do? Yeah, I need one more square brackets, right? Because I am trying to do it in the column. You need one more square bracket. What's the problem? Let's check this. What did I do? Yeah. Did I make a mistake? Okay. But this is not what we want. What I wanted was this all to go into the first row. Hmm? What? No, actually I wanted, no, that will not work. This should be the correct way of looking at it. But I don't know why it's not working. 0 to 55, 0.5, minus 0.5. Somewhere I made a mistake or what. Yeah. That works and this does not works mean I made one small thing. Okay. Okay, for now we'll keep this way, but I will tell you what we can do better. So now you can see that what we have is actually the first row is a red color and the second row is a green color and third row is the blue color, right? So now what we can also do is we can split it across the channels, and that channels will give us the red separately, green separately, and blue separately. Okay. So how do I do that? It's just simply you take that image and then take all first axis elements and second axis element and take only the first channel. What is this gives us? This gives us 25500. That means it gives you the first column, correct? Yeah. Now if you now I'll do one thing. I'll just put it in a list right now, and then take all elements. I mean, take all the rows and columns of the first 2 dimensions, but take only the first element in the inner cell. That's what it says. And then take all the columns and rows. But inside the cell, you have 3 dimensions, right? So in that, the third dimension, you pick it up. So now this is what it is. Okay. So now I have 3 different channels separately. You see that the first one is actually just showing only the red channel. Second one is showing only the green channel, and third one is showing only the blue channel. Okay. Now, you can catch these fellows as like this, so that it becomes red, green, and blue. Now what we can do is we can try looking at each of them. Now remember, what I did is actually I did not do anything except actually picking up only the red channel. So that means it will be 25500. That's what it will be. So you can actually put the color map to gray and to verify what's happening here. Now you see the first channel is actually, although it is what it says that actually the 255 is over here and the rest of them are actually just 0. That means the red is more. That's what it says. The first column has only the red. Or the image completely, actually the red channel is having more red in the first place, and the remaining 2 places actually there is no red at all. That's what it says. There is also another way of easy way of looking at it is using I think it is reds. Yeah, if you give it like this, then it will show wherever the color has been popped up, and it will just make it as red. There are remaining people, it will be a little shade of red. So similarly, what you can do, you can try plotting the green and see this is the green portion of it. If you look at the image, you'll see that. So the full channel is now it been actually got it. Now the red channel is having only the red entries, and the remaining entries are all 0. And the green channel is having only the green entries, and the remaining entries are actually 0. Or in other words, what I'm trying to say is only the red portion has been taken, only the green portion has been taken, only the blue portion has been taken separately. Okay, fine. Now what we are going to do is we are going to actually run a singular value decomposition on each of these channels separately, and we're going to put them together to generate the matrix again, to generate the image again. Okay, that's the plan. Okay. So we'll take one image, then we will do that. We'll do another 5 minutes. So we'll pick up on the color image. Remember, I think we already have picked up one color image, I guess. Yes, over here. Let me take that fellow here back. Now what I'm going to do is I'm going to perform an SVD on each of these channels. Okay. So first thing what I will do is I will actually, let's say, look at the number of singular values that I want to like to look at it. Now you can see that how many singular values will be there here? If you take A transpose, and that will be total of 1000, more than 1400 singular values will be there, correct? That means actually now you need all the 1400 by 1400 matrix to be present in your hand. But now I'm telling that actually now you don't need to do that. You randomly pick up some values. Maybe let's say, well, let's start with 100. So I'm going to pick up only the 100 singular values, and then the corresponding rows I'll be picking up, and then the corresponding columns I'll be picking up from the U and V separately. Okay, so instead of me doing all the three elements, remember what we have here is U into sigma into V transpose actually. But in this, what will I do is I will not pick up all the singular values. Evidently, I will not pick up all the values in my decompositions. I'll be taking only the first 100 columns, no? The first 100 columns, and then the remaining V transpose, I'll take only first 100 rows. Okay, I will explain what I'm trying to say right now. Let me code it. So let's pick some n. So this n is actually going to still number of singular values that I'm trying to pick up. Which one? That's okay for me. Yeah, because I'm going to again multiply it, and that will become positive. That I know. Each entry will be positive, no? Because what you have is these images are all going to give you a matrix A, and you are going to actually decompose that with this U into sigma into V. Now, individually, they may be actually having negative entries in U and V. However, when you multiply back, actually, you should get a positive entry. That is how the decomposition works. Yes. Yes, that's what we are trying to do right now. So I know the idea is very simple. Now, any image we have is actually just simply the matrix of numbers. Now, even if you decompose it, that image is only been decomposed into 3 different matrices. Now, if you put them together, you should get the original image back. Now, the real question is, do I have to put all the 3 matrices together as it is, or I can pick up only a portion of them? That is the question. If I pick up only the portion of it, then what I have done, I have actually reduced to so much of them, right? I did not pick up all the values in my decompositions. So I reduce it and I pick up only the 100 singular values, means I pick up only the 100 columns in the first matrix and then the 100 rows in the second matrix. So totally, what will I do? What will I have is totally of 100, whatever the number of rows I have in the first matrix times 100, that much only is required, and then plus 100 by 100 matrix for the singular matrix, the diagonal matrix, and then again 100 by whatever the number of columns there in the images. So only that much is required for me. So that's what I'm saying. Okay, fine. Okay, let's code that. It's just only a couple of lines. Now let's take a color matrix. Now remember, actually the color matrix is just image, whatever we have just picked up, these puppies. Now for I in the range of 3, you know why I do that range of 3 now? Because I'm going to do for each channel. So for each channel, what I'm going to do, I'm going to split the channel. Okay. The way I actually split the channel is in the following, that I can pick up that channel like this, correct? Yeah. But I think I also need to have the, yeah, I will tell you what I do that. So what I need was a channel. Now this will give me the channel correspondingly, correct? So like yeah. But in the NumPy to work very well, I think I also need something called as, don't keep it just like that, but you keep it as, I don't know what is this called as, contiguous array. How do you pronounce it? Array of that. That's it. NumPy dot as contiguous array. I don't know what you mean by that. Okay. Anyway, I don't know how to pronounce that. Contiguous, right? Contiguous. Contiguous array. So let's keep that as the channel. Now what you can do an SVD on that channel, right? Remember, actually now the channel is just simply a matrix. It's a two-dimensional matrix now. And therefore now we can actually do something extra. Now I understood actually now why is this scribbling is coming up. Somebody else is actually doing it. All these times I was thinking actually and I was only doing it by mistake. Okay. So now let's construct a matrix out of this channel and then do an SVD on it. Hopefully you understand what I'm doing right now. So SVD will give you a U matrix and the singular value diagonal matrix and then the V matrix, correct? Okay. So you take a matrix and then channel spelling mistake. So on each channel, actually now you perform the U SVD. Now, as I said, I do not need all these USV, whereas I just need some of them. So I'll store it as an USV approximation in an array. Now, what I need all the columns and all the rows, but sorry, I need from U, what I need all the rows, but I need only the first n columns. Yeah. And then the second one is in the singular values array, I need all the rows, not all the rows, but until the first n rows. And then I also need first n columns. So the way actually I do that is this way. Hopefully you understand what I'm doing right now, correct? The first n rows and the first n columns I need. That's the first portion over there. And then I need the V transpose. And in the V transpose, what I need to multiply those 100 by 100 matrix, I need 100 rows. Am I right? And every column. Yes. So therefore, first do a transpose and then take 100 rows, the first 100 rows. And then what did I do? I take all the columns, correct? Hopefully that's clear right now. So what is that something that I have done here in this particular row? I did not take all the USV. I took only the appropriate USV for my 100 singular values. So if I took 100 singular values, then what is the matrix size would be, right? I'll print the matrix size if you want. If you know, it's all going to be, yeah, first let's do the computations. Then later I will tell you what does that actually reduced. So now what we can do, now we can recreate the whole image back with this approximations. So instead of actually creating with, we know that U into S into V transpose will give you A back. But we do not now do that. What we are doing right now here is we are generating the image as using these approximated values. So USV approximation. And then take the first one and then multiply that with USV approximation of the singular value matrix that I picked up. And then you take the third matrix and that's all, right? Now you have that product of these right side decompositions. Now what we'll do, actually now we'll make the color matrix replaced by this. So what has supposed to be done? Don't touch the rows and columns. However, what you do is you pick up the channel correspondingly and put these entries corresponding to that channel instead of the original values, whatever was there. So this will give you the correct value. Okay. So let's look at it. Transpose. Yeah, should work like that. What is the problem? Now let me check what's the error. What is it? Attribute error. What is this? Okay, matrix integer dense doesn't have that. So probably what I should do is I should do CDF and then channel. Okay, I understood what's the problem now. Yeah, well, yes, actually it's given me the idea. What I should do is I should actually normalize that image into 0 to 1. Remember I said instead of 0 and 255, I should normalize that image. I believe I can directly do it by color image equal to color matrix divided by, that's a NumPy array. So it's a beautiful thing that we can do is we can divide by a number and it will divide by every cell and every value of that. So that we can do. And now that works. Okay. So now what is happening here is, now if you look at the color matrix, now this has some values like that. Now if you look at the shape of it, is this 3 rows, 1 column? Huh? Okay. The name of the image must be dog. Huh? I was thinking, why is happening actually 3 rows and 1 column? It cannot happen. Supposed to be dog. Could not broadcast the image array to 3 by 1. Here also dog. Yes. Now you see the shape is changing. The image was simply this one, IMG. This one, but what we wanted to was the dog array. So the dog array should be there. Yeah, it does takes a lot of time because the image size is definitely a large image size. So it has to do an SVD on that image, and then it has to put it back together. Yeah. Right. Let's see when it completes. I think after that we replaced it with smaller image, no? 1024. Let's see. So typically what we have done is, let it run. So typically what we have done is, we have a bigger image like this. Okay. Now I know this is actually of size, let's say 1000 by 1200. Now what I did is actually I split this matrix into something of size 1000 by 1000 into something of size 1000 by 1000 again, and then into 1000 by 1200 again, correct? So this is my U, this is my sigma, and this is my V. Agreed? So this is your SVD. Yeah. Correct? So then what we did right now here is, we did not pick up all these values to combine it back. So we did an approximation, and that approximation was giving us only the first 100 values I picked up here. Only the first 100. So 100 of the 100 value I picked up here. And then to have that multiplication properly, I picked up the 100 columns in my hand. So this is just only the portion I picked up. And then to have the corresponding multiplication happen very well, then I picked up only the 100 rows over there. Huh? Yeah, I already assumed that transpose is there in my hand. This is V transpose, obviously. Yeah. Okay. So therefore, now what I have now, so instead of you having 1000 by 1200 entries in my hand, now I have 1000 by 100 plus 100 by 100 plus 100 by 1200. Can you tell me what is these numbers? What are this number and what is this number? It's a very simple, very tough calculation, I guess. Okay, I think I missed one. So this is this number. I don't know how do you read it. Probably some 12 lakhs. And what is this number? This is actually some 1000 and 100, and 100 and 100 is actually simply, what is this number? Can you add and tell me? Just compute and tell me. No? Very simple. We have already crossed the time. 2 lakh. Definitely not 2 lakh for sure. 12 lakhs. 1 lakh 22,000. Yeah. Is it correct? So definitely what I'm trying to say is the number of entries that you have in these three matrices separately is far lesser than what you have in this original matrix. Yeah. I don't know what this number is. I'm not interested in calculating right now. But you can imagine what's happening here is the number of entries that we have in three different matrices together is definitely far lesser than the original matrix what you have. 2,30,000. Okay. So here we need some 12 lakhs entries. However, over here actually now we need only 2 lakh 30 entries. That means the size over here is actually you need 12 lakh bytes, whereas here you need only 2 lakhs 30 bytes. So what we did right now, technically, we have actually reduced the size of the image while sending it to the other people. That's how we do, right? What we wanted was actually now I have some image and I want to send it to you. So instead of me sending the whole image as it is, I will send three matrices to you. Okay. And that three matrices will reduce the size as well. Therefore, actually, the image transmission is actually much easier. That's the idea of doing it. So yeah, now it ran. Now you see that actually this is the return back actually the same size. Size did not reduce, meaning the image size did not reduce, but the memory size actually is while sending it is automatically reduced right now. Okay. Now what I can do is now I can do image, sorry, plt dot im show of that color image now, right? So color matrix. Now you can see what happened here. What happened here? Since I took only 100 singular values, the image has actually become like that. But I know this is actually there are a lot of them are there. So what you can also do is you can take some 600 singular values and try running that and find out what will be the corresponding image. Yeah. $600 is still lesser compared to 1,400. So if you need more quality image later, when you are getting it in your hand, then use more singular values. If you need lesser quality in your hand, then you use less number of singular values. There are ways of actually selecting the singular values what you wanted. There is something called as variance explained by these singular values. If you cumulatively actually find out what is the number, what is the amount of singular values, you can figure it out. Do you need 90% of the variance explained by this image is to be retained or not? 80% is retained or not? 70% is retained or not? Such calculations you can do. And appropriately, you can select the number of singular values. Right now, actually, I randomly picked up one value, but there is a way of actually picking up the singular values as it is. Okay, fine. If you change it to 600, I think it should give you a right image back. Okay, fine. Any questions on that? Probably tea is waiting for us, so we have to go for tea. Good. There's something wrong with that. Oh, it's clipped the value for this. That is the problem. I should probably multiply that with 255 and then still not. Okay, I'll check. But this should work according to me. And it works in my notes, obviously. So it has to work. Yeah, here I'll show you. You see, here's the color image that I have read. And then we have normalized that over here. And this was the image. And the original image size is 1204 by 1880. And what we did here is actually we split the channels as we did in the other one. And then we looked at the corresponding channels over here. You can see that now red, green, blue are actually visible here. And then this is the exact code we have written in the current notebook. Now we have chosen n equal to 100, and then for each channel actually now we split it. We wrote a function called split channels here, which I didn't do it in the other one. So here you have the split channels. Then later what we did, we do a singular value decomposition, and we picked up only those number of columns and those number of rows, and then we built back the image, and that built back image was actually is been constructed like this. So we did not lose much. So you see that this what image was showing was that approximated image only. Oh, probably I did not show that, or what? I don't know. Yeah. Huh? In the code? Yeah. So you understood now what's happening here? Did I made a mistake? Which one? Okay. Hopefully that's okay now. I think we'll break for tea and we'll meet back in 10 minutes for the next session. So it's already 11:25. So we'll meet back by 11:35 for the next session. The next section will be handled by Dr. Vinay. Okay. Thank you so much. See you later.